Good day, I'm Dr. T. Welcome to my office. So I'm jumping into the wonderful world of chemistry, and I'm going to spend a couple of videos on this. The first one, I want to kind of set the stage, talk about kind of the atomic, macroscopic, nice, simple atoms, compounds, that kind of stuff. Then I'm going to expand it into mixtures and chemical reactions in later videos. Like always, I'm going to start off with some future reading, or in this case, future viewing. Complexly, several years ago, actually I think it was before they started calling themselves Complexly, created Crash Course Chemistry, and I do recommend it. It's not perfect, but it's a pretty good, I think 40 some odd part YouTube series. So if you want to dive in deep, it's a nice jumping point. Obviously, this is an entire scientific discipline, so you can dive in as deep as you want. Also, OpenStax has a chemistry textbook that's not too bad, and LibreText is always awesome for whatever they happen to have. Although, navigationally, they're always a little bit weird. Okay, so to start a conversation about chemistry, we got to start talking about atoms. Because chemistry ends up being the study of atoms and the things they make and the interactions they have. Usually you'll hear definitions such as chemistry is the study of chemicals and chemicals are anything made of atoms. So that's basically like everything. Of course, is the classic joke, you know, why can't you trust an atom? They make up everything. Okay, that was corny. But in order to understand chemistry, we need to understand atoms first. The idea dates back to the Greeks, although I don't like giving the Greeks too much credit here because they're kind of guessing. And the general thought is, okay, what is stuff? Oh, there's all this stuff. What's it made out of? And so there, you know, you had the like Aristotelian 5 elements. You know, everything's made up of earth, water, fire, air, ether. China had their own 5 elements. But then you had other thoughts, and one thought comes in is that matter or stuff is made up of little tiny particles you can't subdivide. So basically, if you take a loaf of bread and you just keep chopping it, at a certain point it's no longer bread, or you can't cut it anymore. And so then the idea is that there were bread particles that you could extract from wheat and make into bread. Then you might have wine particles you could extract from grapes and make wine. Once again, they're guessing at things they eventually stumble on kind of not an unreasonable idea. I mean, it's not right. But the Greeks had this kind of standard epistemology of logic and thought. Empiricism hadn't become a thing yet. It wouldn't become a thing for a while. And so they're kind of guessing around. So I don't like giving the Greeks too awful much credit. But by the time we get into the Middle Ages, we start seeing the Islamic caliphates becoming the dominant area of science and technology. Basically, science follows the money. Science is expensive, so throughout history, whatever society happens to have the most money, as long as something really weird isn't going on, they usually happen to be the leaders in science and technology and that kind of stuff, just because money. But we start getting this idea that substances can be broken down into constituent parts, but some things can't be. They are already broken down. And this idea probably does exist around in the Greeks. I'm not too positive on this one, but you definitely really start seeing it with some of the Islamic science and going forward. But this idea, I'm quite certain, was existing around for the Greeks, at least a little bit. You know, otherwise, the atom theory doesn't make any sense if they're coming out of that. But you get this idea, you can't break stuff down. And so people start making lists of all of these unbreakdownable things, what they call elements. And this ends up turning into what we now think of as atomic theory, because we start realizing, okay, there's these elements, we can't break them down. And then it also looks like they're always in these like whole number ratios. We get a guy by the name of John Dalton in the 19th century who comes up with basically the first modern model of the atom. Now, when it comes to atoms, we run with probably half dozen different models. Half dozen's too many. Maybe 3 or 4 different models of the atoms. John Dalton's is the most primitive of these models that we still use. Obviously, we know it's incomplete. by a lot, but it's still useful. And so in John Dalton's model of the atom, he basically says atoms are hard spheres. You can't change one atom to another. All you can do is shuffle them around. Now, we have learned later, you can do nuclear physics. You can do a nuclear reaction where you can change one element to another. But as long as you're not doing any like particle accelerators or radioactive whatever, they're not doing that. So chemistry, we're going to kind of ignore that for the most part. And so you got these ideas, these indivisible atoms. And so now you can study how these atoms arrange themselves. And atomic theory doesn't become like the overwhelming, dominant, this is how the world works model until the 20th century. And actually Albert Einstein weighs in on this with what's known as Brownian motion, where if you have like pollen grains, really little things floating in water, they wiggle and they move in interesting patterns. And the patterns make sense as if water is actually made up of small particles bouncing around. And so this really kind of locks in atomic theory in the early 20th century. So it takes like over a century because Dalton's early 19th and Einstein is weighing in the early 20th century for this to really lock in. Which is just interesting of how long this kind of took. And in some respects, how recent this is. So we get this idea of the atom. And so this then influences chemistry. Chemistry now becomes the study of atoms and how they interact with each other, creating this idea that chemistry is the central science because everything's made up of atoms. Any science other than physics, more or less, is going to be dealing with stuff made of atoms. And even physics is going to be dealing with stuff made of atoms, but they're like dealing with two atoms, so they don't really need to use chemistry too much usually. So the idea here is that if you've got, say, biology is rooted in chemistry. If you've got geology is rooted in chemistry. Geology is also rooted in physics. There's the kind of common joke, geology is physics with trees on top. But you get the general idea. A lot of disciplines, as they go back and kind of like, you keep asking why and how, eventually you get into chemistry. And now chemistry, when we ask why and how, we get into quantum physics. So we're kind of in the middle. We're between everybody else and quantum physics. So we have this area that becomes fairly important. If you can understand how the world works from the kind of atoms on up, that gives you kind of a leg up, and you can start seeing why certain things happen to be. You know, if you study the arrangement of proteins, the actin and the myosin, and what you realize is that the myosin's head only goes one way, and that's why your muscles can only contract, they can't push. And thus you have to have two muscles of everything. So you can kind of dive in with some topics. Now, Dalton's model is kind of the first one that we still use. We still quite often talk about atoms. Sometimes it's called the billiard ball model, as these hard spheres like pool balls. And we'll do that quite often because usually that's enough resolution. We don't need to dive into the atom. But you know what? Diving into the atom tells you a lot because there's a lot of questions like, oh, the atoms do this. Well, why do the atoms do this? Well, you got to crack into an atom. So if we jump into an atom, we get a bunch of different models that I'm going to kind of gloss over. They go from Bohr, which is kind of the second oldest one we still teach. There's a couple between Bohr and Dalton, but we're going to kind of jump into Bohr, and then it goes into Schrodinger, and there's a couple in between ones. And basically, Schrodinger is Bohr's model, but with a whole lot more calculus and a lot more complexity. And I'll get into kind of why. So in Dalton's model, atoms are just hard spheres. But in Bohr's model, what he realizes is he takes the work of others, and Bohr is late 19th, early 20th century. I think he's early 20th century. But Niels Bohr comes up with this idea that he sees the work from Rutherford. Rutherford realizes that all of the mass, or virtually all of the mass, it's not all of the mass, but it's almost, all of the mass of the atom is located in a tiny little speck. And that we have discovered at this point the proton and the electron. Electrons were originally cathode rays. If you've got like one of the old big square TVs, those are cathode ray tubes. Yeah, they're shooting beams of electrons to paint the picture. But we had discovered the proton, we discovered the electron. We had not discovered the neutron yet. The neutron's not discovered until the 1930s, which is rather interesting to realize the lag between discovering the neutron and weaponizing it into, with the Manhattan Project, was a really short period of time. I believe it's around a decade, which is just interesting. Not necessarily a good statement about the nature of humanity, that we felt that was needed. But unfortunately, well, the early 20th century had a lot going on. Let's put it that way. So in Bohr's model, you've got the protons and then later the neutrons are in the center of the atom called the nucleus. And then the electrons are kind of buzzing around the outside. And Bohr would say in orbit, I'm going to use the word buzzing because Schrodinger makes things a lot more interesting with this one. But you've got the electrons going around in kind of a cloud around the nucleus. And there's kind of these layers. And that these layers end up becoming kind of a really big deal. Because it turns out that chemistry is less the study of atoms and more the study of electrons around atoms. So obviously the nucleus has a big impact on the electrons. What we discovered is the things that we were calling elements, these individual atoms that were atoms of that type is because of the number of protons. So the number of protons, what we call the atomic number, is what makes an atom of that element. And basically what's happening is the number of protons influences how the electrons buzz around the nucleus in these rather complicated patterns that we will call orbitals. You got shells and orbitals, and it gets more complicated from there using Schrodinger's model. But the number of protons dictates how the electrons, the shape and the style of the orbitals, as well as their relationship with other atoms and other things going on. So these orbitals will merge and interact with each other. But that's going to dictate the element, is the number of protons dictating the electronic environment where the electrons live. When we discovered the neutron, we actually discovered things were a little bit more interesting because you've got different elements, that's different number of protons. You can have ions, that's where you change up the number of electrons. And since the proton's positively charged, the electron's negatively charged. If you have an equal number of those, you've got, same number of protons, same number of electrons. You got yourself a nice neutral atom. The two charges cancel. They're being held together with electrostatic interactions. Opposites attract, positive and negative attract each other. But you could change up the number of electrons. The protons don't change unless you're doing some nuclear physics stuff. And thus you can get yourself some ions. So cations have a positive charge, anions have a negative charge. Cations have a positive charge because they've lost an electron. Anions have a negative charge because they've gained an electron. Yeah, so when we originally were defining what positive and negative were, we did not know what the electron was. This was 18th, 19th century when we're doing this. We hadn't discovered the electron by a long shot. And so we basically picked that if you rub amber with fur or silk and glass together, you got positive and negative charges. And unfortunately, we could have, depending on which one we picked, we could have made the electron positive or negative, but we picked the one that made it negative, which makes forevermore chemistry annoying to learn because you add negatives, which is really annoying. But you get yourself some ions, and we're going to dive into that here in a little bit if you shuffle around the electrons. Not to mention you can shuffle around electrons in chemical reactions and like that. But also living in the nucleus are your neutrons, and you can get different numbers of neutrons. They don't change out without doing some nuclear physics. So if you've got, say, carbon, you've got 6 protons, that's why it's carbon, but you could have 5, 6, 7, or 8 neutrons very easily in there. Generally, it's going to be 6 or 7, mostly 6, but you can vary these. And these different number of neutrons, we call them isotopes. Iso, same, tope, substance. Basically, whenever you see iso, it's same but not same. And with these guys, they'll have slightly different physical properties, slightly different chemical properties. A lot of textbooks will say, especially lower level textbooks, that isotopes are chemically identical. They're not. Their slight change in mass does change the physics of how things work, and that does change the chemistry. They don't have a big difference. It's usually relatively subtle differences in chemical reactivity and chemical properties, but it's not no difference. So there is a subtle difference between these guys. I mentioned chemical properties, counterpoint is physical properties, and I will talk about this later in one of the later videos where I talk about chemical reactions. But quite often we will talk about the way something interacts with the world around it as its properties. If it's doing so and staying itself, so it's interacting with light or something, we usually call that a physical property. or gravity, mass, etc. But if it's interacting in a way that causes a chemical reaction, we generally call that a chemical property. I will point out that physical and chemical property versus physical and chemical change are ones that, as a professional chemist, I really don't use that much. These are ideas that we talk about more in kind of early education, and then move on to much more advanced concepts of chemical reactions and things like complex formation. And this is one where I do want to bring up a point. This is something I always like to bring up in all my classes. That is, as humans, we build conceptual frameworks. We build these models to put stuff into, but these are human constructs, and nature is under no obligation to comply with the constructs that we've created. As such, we will have nice, neat, clean boxes, nice definitions of things, but in reality, those boxes quite often overlap. So instead of these nice discrete boxes, you get something that looks more like a Venn diagram, with things sitting in between things in the middle. So between physical and chemical change, or physical and chemical property, you have things like complexes. So when, say, an oxygen binds to a hemoglobin in a red blood cell, that's not exactly a chemical reaction. I mean, it kind of is, but it kind of not. It's in this weird field. And then you have other things that just don't fit anywhere within your boxes. So you either need to make a new box, or you just have to acknowledge they don't really fit. So you've got some overlap, you've got some there. Also, there's things that, well, the clean, nice, orderly edges of the boxes saying this is in the box, this is out of the box, they're not there. Nature isn't obliged to follow some law. We just try and approximate what nature does. So not only is our conceptual framework more of a Venn diagram than discrete boxes, it's more of a Venn diagram without the circles. It's just fuzzy blobs. And so don't try and get all hermeneutic, the study of like the text. Don't try and go through natural laws and like analyze like a lawyer would the text really deeply, because the natural laws are descriptive of what we think nature is doing. Nature does whatever nature wants to do. So we've got ourselves some atoms. These things are ridiculously small. So roughly speaking, there is as many water molecules. Water molecules are going to be 3 atoms, 2 hydrogens and an oxygen, that's the H2O, hooked together. And there's roughly as many water molecules in a shot glass of water as there are grains of sand on the planet. These things are ridiculously tiny. And so when we think about them, we want to kind of change up a little bit of our framework, the way we think about them. For starters, if we want to count them, you cannot just do 1 atom, 2 atom, 3 atom, 4 atom. You will not live long enough, I guarantee you. The entire species will not live long enough to do that of any meaningful size, unless you're dealing with like a nanoparticle kind of thing. So we count by weight. And so, of course, now we need to talk about the weight of atoms. As I mentioned previously in my video on the SI system, the unit of mass for atoms is the Dalton. This starts off with Dalton. He basically does the relative atomic mass to hydrogen. And he says, well, a carbon is 12 times heavier than a hydrogen. And this is kind of the beginnings of this. By the mid-20th century, we come up with the atomic mass unit, which is now a defunct unit. And the idea of the atomic mass unit is that it is 1/16 the mass of an oxygen atom. So it ends up being the same as a hydrogen, but we're dealing with oxygen, not hydrogen. Easier to work with. But things are a little bit more complicated. One, there's a bit of a debate. Chemists have an atomic mass unit of being 1/16 the mass of an oxygen atom, whereas physicists have it being 1/16 the mass of an oxygen nucleus. Well, almost all of the mass is in the nucleus, so those two numbers are almost the same, but they're not. The electrons do have mass. They don't have much, but they do have mass, and most of the time we can ignore them, but not all the time. And having 2 different units with the exact same name and used the same way could create problems. But this worked fairly well. We also created the concept of the mole, or Avogadro's number worth of something. As I mentioned Avogadro's number back in the previous video, where it was a conversion between kilograms and Daltons. And so roughly this was 1 kilogram divided by well, I should say 1 gram divided by 1 Dalton. And this meant, though, that you could look on a periodic table, look up the mass of your atoms, add them up. That was the mass of, say, 1 molecule or 1 formula unit, and then divide the grams you have by that number, and that's how many moles you have. Pretty straightforward, actually quite helpful. Now, as I mentioned, the atomic mass unit is now defunct. There were the whole, which oxygen are we using? That was a bit of a problem. And then there was another problem, as we hadn't realized that there were oxygen isotopes. And turns out there's oxygen isotopes. So not only which oxygen are we using, with or without the electrons, which type of oxygen are we using? So the result was we created a new unit. This was the unified atomic mass unit. We unified chemistry and physics. Chemistry won this argument. We got to keep the electrons. And so this is the unified atomic mass unit. This was done roughly in the Reagan administration. We then renamed that to the Dalton, bringing back the roots of John Dalton. We name a lot after John Dalton. He's kind of a big deal in chemistry. Discovering the atom, or really coming up with a modern theory of the atom, is kind of a big deal, shall we say. Now, the other thing Dalton starts working on, and we've actually been working on since the past, is this idea that, well, we've got these atoms, we need a shorthand of doing this. So if you look at Dalton's kind of original list of atoms and his explanation of atoms, you start seeing these kind of shorthand symbols. And we've been working on that since the alchemists in the Middle Ages, of doing these nice shorthand symbols. But these are going to evolve as time goes on. Because weird squiggles are nice and all, but they're easy to write, but they're a pain to type, especially if you got movable type. You don't want to have to make a bunch of weird symbols. If you could just use letters, that would be nice. So we start giving atoms symbols based on just their name, and it's going to be an abbreviation. So certain elements, like fluorine and oxygen and carbon, they just get their first letter. Pretty straightforward. Other elements, though, well, there's 118 elements. It wasn't back then. We didn't know of all 118, but now we know of 118, and, well, there isn't 118 letters, so we had to use 2-letter combos. So things like cobalt became CO, barium became Ba, and that kind of stuff. Of course, these are the names in English. Some languages use slightly different names, and sometimes those languages use their letters. So iron is Fe for ferrum, iron in Latin. Tungsten is W for Wolfsven, which is, I believe, the German name for that. Now, we got 2 letters. One's going to be uppercase, one's going to be lowercase. We do that because there's no punctuation. If you're looking at an older periodic table, or possibly a future periodic table, you might see some elements being listed as a 3-letter symbol. Those are temporary ones. Basically, we've discovered the element. We haven't officially gone through the naming system yet. Basically, what happened is during the Cold War, the US and the USSR both discovered the same element, both gave it a name, not the same name. Possibly the same name, 2 different elements. Actually, that was a case for that. As such, we needed to sort that out. So we agreed, we'll put a temporary name that's based off an atomic number, and that'll be 3 symbols long, and then once we get a name, we'll replace that. In 2026, there's nobody with a temporary name. Future, don't know. Past, obviously, there has been quite a few. So as I mentioned, the study of chemistry is basically the study of electrons. In general, one of the most important features of the electrons are the ones that are on the outermost layer of the atom. Atoms are arranged in shells, or kind of layers, and each one's kind of subdivided, and this is Schrodinger's theory. Well, how the outermost layer of the atom is arranged ends up greatly impacting the chemistry of the atom. So we call that outermost layer the valence layer, or the valence shell, or the valence electrons. We usually don't call it valence layer. It's valence shell, or the electrons in there are the valence electrons. The inner ones we call the core. So before we discovered electrons, and basically as the idea of atoms is quite new, we discovered there were some patterns. Various elements were all relatively similar, and if you put them in order of weight, remember, there's no atomic number, there's no protons discovered yet. That will take a little bit. This is 19th century. Dalton's figure out what atoms are. We're still working on what's on the innards of those things. But it's realized if you take the weights, because we can figure out relative weights relative to hydrogen, and then eventually we move into the idea of the atomic mass unit, later the Dalton. But if you arrange them by weight, what you'll notice is that there's kind of this repeating pattern. that you've got somebody like fluorine. It's got a series of physical and chemical properties. And then several elements later, you have chlorine, which is not quite the same, but very similar. It does similar chemistry and whatnot. And then several elements later, you've got bromine. And again, it's different, but it's awful similar. And so what was realized is that there was something going on with the elements, and there's this repeating pattern. And of course, metaphors to like octets, etc., are being made with these. And so during the middle of the 19th century, there's this big push to try and organize all of the elements. Instead of just a list is nice, but could we do more? Could we discover more information? Because as you organize stuff, you might be able to see patterns in what you're organizing. And thus begins the push to create periodic tables. Now, depends on what stories you want to read, the periodic table evolves over the 19th century. And it starts out relatively primitive, just kind of as lists, but then we start making it more advanced. We get things sort of like these drum-shaped periodic tables as we're looking at the repeating pattern. Usually, the guy that gets the most press is a Russian chemist by the name of Mindov. He and the P guy have almost the same name, so it's always awkward saying it. Anyways, what he realizes is he's listing out the chemical and physical properties. He's trying to organize the table of elements. He comes up with the kind of really profound implication that, wait a minute, maybe we don't have a full deck. He's literally making them cards, and he's dealing with decks, and he's like, maybe I'm not playing with a full deck. Maybe there are elements we have yet to discover. And so he starts laying out, and he leaves gaps. One of these gaps is going to be germanium and gallium, or would later be germanium gallium. And what he does is he starts predicting their physical and chemical properties. And when those are discovered, they line up uncannily close with what his periodic table suggested they would be. This is kind of a big deal. This says you're on to something when you're able to kind of predict future discovery. And so now we've got the periodic table. The modern version dates to the 1960s. Obviously, it's been updated with new elements as we've discovered them. The general shape, though, is actually based on the valence shell. So the columns, we call those families, and they're going to have relatively similar chemistry. They have similar chemistry because their valence shells are generally relatively similar. And the rows, we call those periods, and that ends up being describing which shell is the valence shell. So the electrons are in layers around the atom, and, well, the outermost layer is your valence shell, and the period is generally giving you the information on what your outermost layer is. Now, we've talked about atoms. Let's stick them together. I already mentioned water. If you stick multiple atoms together, you're now going to start making compounds. I should say multiple atoms of different elements. If you stick multiple atoms of the same element together, we call that its elemental state. If you've got different ways of arranging them, we might call those allotropes. Allo meaning different, trope meaning substance. Basically, if you've got carbon, you could have diamond or graphite or buckyballs. We would call those allotropes. But most of the press goes to the compounds because there's a whole lot more compounds. And in this case, you're going to arrange atoms together and you're going to make a new substance. In this case, we're going to be dealing with pure substances. The next video, I'll deal with mixtures. But pure substances are either going to be just the element or just a compound. So one arrangement of atoms. And we're going to be consistent with that particular arrangement of atoms. Now, compounds can be arranged in a couple of different approaches. And by the way, I should point out that what I'm going to dive into generally goes into topics that are more high school chemistry level, but I think you need to know it. Actually, most of this video is definitely things that are a little bit more high school chemistry relevant than, say, elementary or middle school, but you got to know more than what you're trying to teach. So that's why it's in the video. But if we've got these guys, we can kind of categorize our compounds. Once again, categorizing, it's really a fuzzy Venn diagram. But we can categorize them roughly in about 3 different buckets. And if we look at the periodic table, The left 2/3 are what we call metals. Typically, they're pretty good at sharing their electrons. They're going to form a metallic bond if we get them together, which is basically like an electron commune. They're going to share some of the electrons. Their valence shells are going to start merging together to form these large, elaborate energy levels, what we call bands. And as such, the electrons can kind of float freely, at least some of the electrons can. And this gives you all the properties of metal. It conducts electricity nicely because the electrons can move. It conducts heat fairly well for the same reason. It's shiny because the electrons can wiggle around and interact with light and thus be nice and shiny. And so if you get multiple metals together, you have a metallic bond. Generally speaking, you make different metals together. You don't really get compounds, you get alloys, which are something I'm going to deal with, I believe, in the next video, but they're definitely in that fuzzy area between not really a compound, not really an element, not really a mixture. Well, they're definitely not an element, but not really a compound, not really a mixture. We categorize them as mixtures, but they're weird. Now, on the right side of the periodic table, we've got ourselves the nonmetals. These are going to have basically the opposite properties. They tend to form covalent bonds. Their orbitals will overlap, they'll merge, but they don't form this giant electron sea, no like giant electron commune thing going on. Metals do electron seas. For the most part, nonmetals don't do this. Instead, they form these discrete sharing relationships that we call a covalent bond. Now, because it's discrete electron sharing relationships, the electrons can't flow. They're trapped between two different atoms. So with the major exception of graphite, which actually does create effectively a two-dimensional electron sea. It's not three-dimensional, it's two-dimensional. It's really kind of cool. The electrons are more or less locked between the two atoms, and so they can't flow, so they're lousy conductors of electricity. Graphite, which is made of carbon, which is a nonmetal, is actually an excellent conductor of electricity, which is kind of cool. They're generally not particularly good at conducting heat, some more so than others. And generally they're going to be dull and they're going to be brittle. Metals, you can kind of bend and flex and smash them. We call it malleable and ductile. Beat them into sheets, stretch them into wires. You try and do that to a nonmetal, odds are you're just going to get a powder. You're not going to be able to stretch it around because that electron sea can kind of flex and the electron's going to rearrange and the atom's going to rearrange, and you try and do that with a discrete relationship, you just break them. So you're not going to be able to pull a block of diamond into a wire. That's not going to work. Now, if you get one from one side and one from the other, you get some rather interesting ones. Generally speaking, metals hold on to their electrons not as well as nonmetals. Nonmetals generally hold on to their electrons fairly well. We call this electronegativity. So if you're trying to share electrons, nonmetals are generally more electronegative. They're going to hog the electrons, whereas metals are lower electronegativity. Kind of makes sense. You get the discrete relationships that's trying to hog onto it, where you got the shared electrons, you're not hogging onto it nearly as much. Well, if you put those together, what ends up happening is that the nonmetal will generally hog, to the point of theft, the electron from the metal. Now, a lot of books will describe it as that individual metal ion losing its electron to that individual nonmetal ion, and that's usually not the case. Usually the metal ion is a cation at this point. Well, it's an ion, and if it's an ion, it's probably going to be a cation. If it's a metal, it doesn't have to be. It usually is. And so it's lost an electron. It probably lost that electron a long time ago. And then you've got the nonmetal. It'll probably be an anion in this case. It gained an electron. It probably gained an electron a long time ago from somebody completely different. And so now you get this electrostatic charge. And so they'll stick to each other with ionic interactions. So we'll sometimes call this ionic bond. This is not, it's always ionic bond in air quotes, because a bond implies shared electrons. In this case, unless it's something like magnesium chloride where there's a large amount of covalent character, because remember, everything's a Venn diagrams, there's some overlap, then the electron's on one side, not the other, so they're not really sharing the electron. Now, in all reality, basically every ionic bond's got a little bit of covalent going on, so there is some sharing of the electron, even if it's not really that big of a sharing. It's really much more of being separate. There's still a little bit of sharing going on. There are chemicals like magnesium chloride in which they're sharing a lot. So it would be wrong to say it's not covalent. It's definitely kind of covalent. Because once again, everything's a fuzzy Venn diagram. Now, if you're dealing with these guys, your Ionic compounds, if they're a solid, tend to arrange themselves into an alternating repeating pattern called a lattice. The lattice is the pattern. The fact that you have a pattern with a bunch of atoms means that they're in a crystal. So the physical thing that's got a pattern is a crystal, and then the arrangement of the atoms in the crystal, the mathematical description, is the lattice. Ionic compounds do this quite a bit. Now, you can have liquid ionic compounds. Those totally exist. They're not very common, but they totally exist. Metallic compounds typically also form a lattice as well. And this would be like the grain structure if you're talking about metal. Each grain is a nice little lattice, and it kind of gets disrupted on the edges of the grain. Metallurgy has a whole lot of controlling this. Now, quite often we draw the lattice as a face-centered cubic. That's what table salt is. It's so much easier to draw. So much easier to draw. I can do a face-centered cubic. I cannot do any of the other ones. But there's actually a whole host of different arrangements for this. So you can have more of a hexagonal approach or a more irregular shape arrangement. Now, the lattice can have a profound impact on fields such as geology, where the arrangement of atoms in the lattice, so the crystal structure, can have a profound impact on the physical and sometimes even chemical properties of, say, the mineral or whatever chemical we're dealing with. Now, when it comes to nonmetals and nonmetals, covalent compounds as well as allotropes of, say, carbon, these can arrange themselves in the form of a lattice as well. Generally, lattices, the mathematical model is kind of repeating forever. Obviously, you run out of atoms, so it doesn't go forever. You run out of atoms, but you have this kind of repeating pattern. They can do that, or they can clump themselves into small discrete units, what we call molecules. So a water molecule is one oxygen. It's got two hydrogens attached. It kind of looks like Mickey Mouse ears, and that's it. Now, you can have two water molecules, but they're separate. They're not directly connected. Now, depending on your conditions, if you cool them down enough, ice is, made of water molecules, and the water molecules arrange themselves in a lattice. So you may see a lattice. However, you also might see an amorphous configuration in things like silicon dioxide, sand or glass, where it's just kind of a chaotic, random, large-scale order. So it's relatively structured on the very small scale, but on the larger scale, it's not. So I'm going to wrap things up. All the lights keep turning off. So I'm going to wrap things up. I want to talk about a couple more points real quick. When we talk about molecular or empirical formulas, we're talking about, in the case of an empirical formula, the ratio of atoms in the compound. This is relevant for things like lattices. So sodium chloride NaCl, that's an empirical formula of 1:1. We're not trying to describe the number of sodiums and chlorines because it's the size of your crystal kind of thing. It's not a discrete unit. It's got a lattice. If I've got magnesium chloride, that's MgCl2. It's one magnesium for every two chlorines. Once again, it doesn't have to be a 1:1 ratio. We can even get ones where you've got an ionic compound where one of the ions is actually a molecule. So something like calcium carbonate. Calcium is a metal ion, and carbonate's actually 4 different atoms stuck together in what we call a polyatomic ion, which is basically a molecule with either too many or too few electrons. In this case, it's got 2 extra electrons. And we call that a carbonate. It's a carbon with 3 oxygens around it. And they've got covalent bonds, but then that's its discrete unit, and so now it's acting as an ion, which, it is. So if we're doing ratios of ions or ratios of anything that doesn't have a nice discrete molecule, we usually use empirical formula. Molecular formula is the number of individual atoms in a particular molecule. So if I've got a molecule of water, I've got 2 hydrogens and 1 oxygen, so H2O. If I've got a molecule of, say, sucrose, that's going to be 12 carbons, 22 hydrogens, and 12 oxygens. That's not a ratio, that's a total, where an empirical formula would have just been 1, 2, 1 kind of thing. The last one I want to bring up is the wonderful world of polymers. So this is going to be mostly, I think I'm going to use the word mostly, because generally you'll learn in science, there's some weird exception to everything you want to say. But this is going to be for generally things made up of carbon or your nonmetals. most commonly carbon though, where you can make a nice little molecule. We're going to call that a monomer. And we're just going to call it monomers. Mono means one and mer means molecule. But then you can take two of them and stick them together. And we create what we call a dimer. And then you can take another one and stick it together. Now we call it trimer. And you can stick several of them together and kind of forming a chain. We call that an oligomer. And you can stick a whole bunch of them in a chain. We call that a polymer. So classic case would be your carbohydrates. You know, glucose is a monomer. Something like sucrose would be a dimer. And then something like starch would be a polymer. There are oligo-sized, kind of the medium ones, a dozen or so. Those we call oligosaccharides. And if you take a biochemistry course, you'll dive into those at least a little bit. Your blood groups are going to be oligosaccharides. But of course, polymers are also famous as being plastics. It's where you've got your polymer. They're going to form this generally amorphous. Doesn't have to be. It could be a crystalline structure or some blend, partially amorphous, partially crystalline. And they kind of flex around a bit. But you've got these nice long polymers that make up what we think of as, plastics. There's actually an incredibly large diversity of these things. It's not just plastic. There's hundreds of different plastics out there. Okay, so I've had to swap out batteries already. We're probably heading close to the hour mark now, if not at least 45 minutes. So probably time for me to wrap up this module. I'll jump into mixtures in the next video. But until then, have a wonderful day and have fun studying chemistry. I'll see you next time.